Okay, so here we're going to do a very brief overview of shifting and stretching graphs. So I'm assuming in this video that you've seen this before, so I'm just going to touch on it very briefly. If it's not super familiar to you, I recommend breaking open a pre-calc book and studying up on it a little bit because it's not a huge part of calculus and I don't want to spend a ton of time on it. The idea here is we start with a base function, in this case f of x equals absolute value of x, and then we do all kinds of things to it, right? We can shift it up, we can shift it down, we can shift it to the left and right, we can reflect it, we can stretch it, we can shrink it. So let's go through these quickly and just see how all these transformations go. Okay, so here's our base graph, f of x equals absolute value of x. That's probably something you should be able to graph without plotting points. Now for this first transformation, we have f of x equals absolute value of x plus 2. This plus 2 is going to be up by 2, right? And minus 2 on the outside of the function would be down by 2. And there we have it. The graph is shifted up by 2 units. For the next one, we have f of x equals absolute value of the quantity x minus 2. Well, when you have a minus inside the function, notice how it's inside the absolute value, it shifts it to the right. So it kind of goes the opposite way of what you might expect unless you spend a lot of time kind of thinking deeply about this. But when the minus is inside the function, it goes to the right. If it were a plus inside the absolute value like this, it would go to the left. And there is our function, our original function, the absolute value function, shifted 2 units to the right. Okay, how about the next one down here? We have f of x equals negative absolute value of x. So this is a reflection. It's a vertical reflection because it's outside the function. And a vertical reflection will take our original function and flip it down, essentially rotating it, the whole thing across the x-axis. And there we have it. Our original function is rotated down across the x-axis to create that new function, negative absolute value of x. Okay, moving on to the next one down here, we have f of x equals the absolute value of negative x. So that's going to be a horizontal reflection because the negative is now inside the function, in this case inside the absolute value. Now in this case, since our base function is the absolute value, which has symmetry about the y-axis, when we flip it horizontally, nothing's going to change. Here it is, and indeed it looks exactly like our original function f of x equals absolute value of x. Okay, for the next one down on our list, we have f of x equals 2 times absolute value of x. For that one, since 2 is a number greater than 1 outside of the function, and the absolute value in this case, that's going to be a vertical stretch. And then if this 2 out in front was instead a number between 0 and 1, that would be a vertical shrink. But in this case, it's greater than 1, so it's going to stretch that whole function vertically, kind of make it more narrow. It looks like this. Essentially, we've taken our absolute value function and grabbed each end of it and pulled it vertically to shrink it into a, I guess, more of a V shape. The last one, f of x equals absolute value of 2x, is a horizontal shrink. And it's a shrink because 2 is greater than 1. If it was between 0 and 1, it would be a horizontal stretch. So again, once the number goes inside the absolute value, or inside the function, I guess said more generally, it's essentially the opposite of what it is when it's outside. So now we have a bigger number inside. So what that does is horizontally shrink things by a factor of 1 over 2 in this case. So take your number, and then 1 over that is the factor by which it shrinks it by. So what this means is every x value is divided by 2, but the y value stays the same. And the effect of that in this case is actually the exact same graph. And that makes sense because we could factor a 2 outside of this function and get the same 2 absolute value of x. So we'd expect these graphs to be the same. You may ask, well, then isn't it always the same? Well, no, when you can't factor the 2 out, essentially when it's not a linear function, then these two things will be different. In calculus, we will spend a lot of time learning new graphing techniques, but they're much different than what we're doing here. So If you're feeling slightly limited now on all your techniques that you have for graphing, don't fret, we'll get a whole new basket full of techniques and we'll be able to graph a whole lot of functions after a few sections.